Welcome students to another Mr. Rich Q&A. It is Sunday, September 15th, and I've got several students here. I'm glad that you're here. Sorry that I got started late. I was running late with another class and am just now making it here. All right, here's what we're going to do today. We're going to jump right in to working some problems. And let me see who all is here. So all right, I have some calculus students here. All right, I like to see that. I have some calculus problems to work. And give me just a quick sec here. I'm going to share my screen. Seeing as I've got two calculus students here, I think I want to start with doing some calculus tonight. I think that would make a lot of sense. So I'm going to come down to my AP Calculus stuff for tonight. What I did for the AP Calc students tonight. Oh, and by the way, of course, this is called Mr. Rich Q&A. So if you have questions that you want me to answer, if you've been working homework problems this week that you're like, if I could have Mr. Rich explain this, I would make a big leap forward. I want to know what the question is. You can post your question into our Zoom chat right now, or you could also email it to me. If you wanted to email me on your phone, a picture of a problem maybe. My email address is askmrrich@gmail.com. I'll put that into the chat here, and I have that email up. So if you do send me something there, I will see it, and I can work that problem for you. Otherwise, for the calculus students, I picked some problems that I think that maybe would be about where you would be right now in your class. I wanted to work some product and quotient rule problems for you. The first problem that I have is a very common kind of problem that you might see maybe in a multiple choice, maybe possibly a free response kind of question. And this is it. It's asking you to take the derivative, right? ddx means to take the derivative of the thing inside the parentheses or the brackets. And they're telling you up here that u and v are functions of x. So these are not constants. These are representing functions. That means then that if I'm dividing two functions, v and u, and I'm taking the derivative of their quotient, of their division, but that's not how we take derivatives when it comes to quotients of functions of x. So can't do that. We have to use the quotient rule. And so I'm going to show you how to do this. Now, I do want to show you the quotient rule in terms of the saying that we use. Now, as you've gone through your math career and algebra, teachers have told you little jingles about how to memorize things like SOHCAHTOA. And I don't know, there's some sayings for even the quadratic formula, which I don't even know what they are, but like keep, change, flip, these little sayings. Well, actually, there's one in calculus that I've used for 30 years when I take the derivative using the quotient rule. All right. And every time I use the quotient rule, this saying goes through my mind so that I get it right every single time. And the saying is, your teacher's probably told you this. Most of you have heard it. It's called low d high minus, that's not really part of the jingle, but that's part of the formula. Low d high minus high d low. And here's the rhyme part, square the bottom, off we go. Every time I use the quotient rule, that saying is in my mind so that I lay it out exactly correct. So low means the bottom, d high, obviously the derivative of the upper, minus the upper part, the numerator, times the derivative of the lower. And then on the bottom, I put the square of the bottom. In this case, it'll be u squared. So when I take this derivative, I simply say low d high, which would be v prime, minus high v times u prime all over u squared. And then it's just a substitution. Right now I'm going to go back. They told me what all of these values are. And I'm doing this derivative at x equals 1. So u of 1 is 4. So there's my u. So this is a 4. V prime of 1 is a 6 minus v. Where's v? V of 1 is negative 2. U prime of 1 is negative 3. And then u squared, u is 4. So I'll put 4 squared. Now, I'm going to tell those of you that are in calculus, I think 2 of you that are here are in calculus. This applies even for non-calculus problems. Right, one of the frustrating things really about algebra, certainly is going to be true in calculus, is frustrating is knowing the calculus, but you got a problem wrong because you messed up the algebra or the math, right? So you have to have a system for solving these problems that you're comfortable with that gives you a high percentage of getting the algebra and the math right. I make mistakes when I do algebra and math, but the system that I use is that when I do employ, say, the quotient rule or the product rule, which we'll get to in a bit, I will write down the resulting algebra. Then I will do my substitution, being very careful to put the things that I'm substituting in parentheses. Now, this is true for algebra. Anytime you're substituting a number or even another function into a function, you're making substitutions. You put the things you're substituting in parentheses, because if there's minuses, you don't want to lose track of the minus and how it's going to affect the calculation. So notice that when I did all of these substitutions, I put things in parentheses. So now I can use my order of operations. 4 times 6, 24. Okay, now I'm going to go ahead and do this all in one shot right here. It's a negative times -2, which is +2, times a -3. So that nets out to a -6, -6, all over 16. So this is 18 over 16. All right. Now, if you see me make a mistake, right, I need you to call me out on it, right? So be sure. Now, let me pull up my chat window here. I need to make sure. Give me just a second here, students. I'm going to pull up my chat window so I can keep an eye on it. Okay. There we go. Let's go back. All right. Let's keep moving on. Now, could I reduce that? Sure. 9/8. Let's move on. This is going to be, now I'm taking same problem with the same prompt up there. I'm going to be taking the derivative of this. Now, one of the reasons why they like to give problems like this, where there's really very little use of the power rule. They're just, number one, testing you on, do you know the product and quotient rule? And also, it's a good way for them to test you on whether you know the properties of derivatives. In other words, when we take derivatives, we can take them term by term. So I'm going to take the derivative of this minus the derivative of this. They're basically two separate derivatives. But when I take this derivative, I have to use the product rule. All right. Now, when I use the product rule, here's what I don't normally write it down, but I'm going to write down what I'm visualizing. Okay. I know that if I have two functions being multiplied, and I'm going to call the two functions f and g, and I'm going to take the derivative of their product. Here's the formula that I use. I always take the derivative of the first times the second. So f prime g plus, and then f g prime. Now, I know some of the formulas would write that as g prime f, but I like to keep them both fg, f prime g, and then fg prime. It just keeps it better straight in my head. Now, what I do if I'm going to employ the product rule, which I have to right here, what I do is I do literally on my paper say, okay, that whole thing is the f, and that whole thing, well, that not whole thing, but that thing, the v, is the g part of my product rule. When I take this derivative, then f prime would be 3u prime, right? The derivative of 3u is 3u prime, and then times g, which is the v, plus, then I take the f, which is 3u, times the derivative of the second, v prime. Then there is a minus 2v prime. So this right here is just a negative 2v prime when I take its derivative. One of the things that students ask me when they start using the product rule is they say, how come, Mr. Rich, you're not using the product rule right here? Because that's 2 times v. Well, you could use the product rule, but it'd be wasting some time because 2 is a constant, right? 2 is not a function of x. So when you got to the point in the product rule where you were going to take the derivative of 2 times the v, well, the derivative of 2 is 0. So we're just recognizing that 2 is a constant. So therefore, it really is not involved in the derivative since it's a constant multiplier. It's just going to end up being a negative 2 times v prime. And then we would go back and we would plug in the values for each of those functions or the derivative. and it would look like that. I'm not going to go get those numbers and plug them in. That's just a simply go get the numbers from up here, plug them in, and don't mess up the math. Okay, let's move on. Again, if you got any questions, or if you think I made a mistake, or if you're like, wait, Mr. Ritz, go back. I didn't see what you did there. Let me know. Okay, put it in the chat and I can go back and cover it more fully. All right, let's talk about how to write equations of tangent lines. Here they give you two functions, f and g. They've given you selected values of the function at 3 values of x, but also they gave me values of the derivatives of the two functions at those same values of x. Then they define a totally separate function called s of x, but s of x is some combination of the f and the g function as they show right here. They want me to find s prime of -1, and then they want me to write the equation of the tangent line, presumably to s of x, at x equals 1. Well, let's take this first part here. I need to find s prime of -1. Well, what I'm going to do is I'm going to first find s prime of x. And I'm going to have to use the quotient rule because I'm dividing two functions of x. So I'm going to use low d high minus high d low, square the bottom, off we go. I'm going to start off with a big gigantic fraction because I'm about to write the whole thing out. Low f of x times d high, that would be times -2 g prime of x. Notice that I wrote the -2 in parentheses so that I can remind myself when I get to the point of doing my calculations that I know that it's a multiplier, not a subtraction, all right? So low d high minus high -2 g of x. So there is, and I go back. As I'm doing this, I even go back to the beginning. Low d high minus high times d low all over f of x squared. Now I'm going to do s prime of 1. Now, a lot of teachers and students, maybe they will skip this putting the x's and they'll just put the 1's in. That's fine. But at this point, I'm now going to go get f of 1. f of -1, rather, right? We're doing s prime of -1. So, okay, all right, I see you emailed me a photo of a problem, and awesome. That's what I'm talking about, right? That's what I want to see, photos of problems here. Awesome. All right, then, so f prime of f of -1 is a -4. Sorry for the noise out there. My granddaughter is over here. G prime of -1 is a -1 minus, look what I'm doing here. I'm not taking any shortcuts. I'm doing my substitution here. G of -1 is a 1. F prime of -1 is a 2. F of -1 still is a -4, and that's squared. I'm not going to go from there. At this point is just do the calculation, right? And not mess up the signs. There's always going to be ample opportunities for you to mess up a sign in your math calculation there. Okay. All right. Now this, let's see. I wished I knew the number to this, but I'm going to, you know what? I lied. I'm going to calculate this out. This is going to be, I'm going to go with -8. This is going to be +4. That looks to be -8. This looks to be +4, while this would be a 16. So hold on just a second. And then this would be -4 over 16. So it looks like it's -1/4. The other part of this problem is writing the equation of a tangent line. Every time in AP Calculus that someone tells you to write the equation of a line, could be a tangent line, a normal line, you're going to always start with point slope. Hopefully your teacher has shown this to you. If you're in Florida Virtual, hopefully they're teaching you that. Okay, so that is how we write equations of lines. We don't use slope intercept. We use point slope because this is a much more flexible version of a linear equation. I can put any point in. I don't need the y-intercept point. Well, the -1/4 is the slope of the s of x function when x is -1. So I'm using the result here to put in for m. So this is going to be a -1/4. Now, what do I need? I do need to know the point of tangency. Well, I know that the x value is going to be -1. So that means that this is going to be x minus a -1 or x plus 1. but I have to go get the y value for the point of tangency. So I've got to find out, I'm going to do the work up here. I need to find out what is s of -1. I need to know the y value of my s function when x is -1. This is the definition over here of s of x. So s of -1 would be -2 times g of -1 all over f of -1. So it's a -2. G of -1 is a 1 divided by f of -1 is -4. That looks to me to be a positive 1/2. -2 times 1 over a -4. So this answer would be y minus 1/2 equals -1/4 times x plus 1, like that. All right, and that's going to be the equation of my tangent line at x equals -1. Questions or comments? Put them in chat. All right, I have a question. Let's see if this works. I'm coming over here to take a look at this problem. And what I'm going to do is I'm going to copy it over. Let's try it. A student has requested this problem to be worked. Hopefully you all can see that. That looks to be like a natural log in there. Okay, I love this problem because this always stumps students, not this problem in particular, but these types of problems. I'm going to rewrite the problem here. The limit as h goes to 0. I'll write it off to the side here. This is saying the limit as h approaches 0 of the natural log of e plus h minus 1 over h, like that. And then they get, this is a multiple choice problem. They're asking you, or no, let's see, oh yeah. So they're wanting us, it's a multiple choice problem, but we're going to figure this out. I'll show you. Now, you would think when you look at this that they want you to evaluate the limit. No, they actually don't want you to evaluate the limit using your tools from Unit 1. What they are wanting you to do is to recognize that this is the limit definition of a derivative. I'm going to show you the limit definition of the derivative of a function at a point called a, where x is equal to a. And you all, if you've made it this far into Unit 2, you know this definition, or you're supposed to know this. It's f of a plus h minus f of a all over h. This is a formula. It's a limit definition of the derivative of f of x at x equals a. So what your job here is to say, wow, this question that they've given me is the derivative of what function at what x value? Well, notice, I think I know what they're doing here, because the function, this is supposed to be, in this position, is supposed to be f of a plus h. I think that that's the a, and that the natural log of x would have been the function. So they want you to like reverse engineer this to say that if someone had told you, I want you to find the derivative of the natural log of x, and I want you to find f prime, its derivative at a value of e, you know what you would have gotten? You would have gotten this, because you would have put the e in for a, and then you would have put the a plus h in for the x so that it's the natural log of that. Then you would have said, well, what is the natural log of e? So you have to know that, hopefully you know this, class, that the natural log of e is equal to the number 1. That's why there is a 1 right there, because f, in this case, if this is my f of x, f of e is the number 1, which is why there is a 1 right there all over h. So now that I know that the thing that they're showing me in the problem is really just the derivative of this function, well, I know what the derivative of natural log of x is. If your teacher has gotten that far, you know that the derivative of the natural log of x is 1 over x. You say, where did that come from? Well, it's just something to memorize. Okay, the derivative of the natural log of x is 1 over x. And therefore, f prime of e is 1 over e, like that. So we go look at our answers, and let's see what we got. And so it's f prime of e. Now, I can't hardly see the primes on there, but it looks like that must be f prime of e. And therefore, where f of x is the natural log of x, that's going to be my answer. So you have to get practice reverse engineering a limit definition of a derivative so that you're not really evaluating the limit. You're just recognizing what it represents and then using your rules of derivatives to take the derivative of that function. So I hope that helps to my student who posted that photo of a problem. All right, let's move on. Let me see what else I have. That's pretty much it for what I was going to cover on calculus. I'm going to talk about pre-calculus. And I'll tell you what, if you're in calculus, this discussion is not going to be a bad one. This one's going to be, I think, a pretty good one for you because we're covering it in AP Precalc right now. We're covering rational functions and all of the attributes of rational functions. And I'll tell you, this is a lot easier when you understand rational functions and you can visualize what the functions look like and what their behaviors are. Vertical asymptotes, horizontal asymptotes, holes, so forth. So what I'm going to do is I'm going to take this problem. The problem I'm working here really, I guess, goes from about 1.7, encompasses everything from lesson 1.7 to 1.10 in the AP Precalc class. So this doesn't tell you what we're going to do. So here's what we're going to do with this function. We are going to do the following. We are going to determine the domain. We're going to the zeros, its x-intercepts. If it has any vertical asymptotes, does it have any holes? What are its end behaviors? Like what does it do way out on the extremes? We're going to determine if there are horizontal asymptotes. And we're also going to use limits to justify whether there are vertical asymptotes, holes, or horizontal asymptotes. So if you're in calculus, you've been doing limits, and so you'll maybe find this of interest and a good refresher on rational functions. Well, the first thing I'm going to do in this case is I'm going to go ahead and I'm going to factor both the top and the bottom. Well, there's not much to factor on the bottom. It's already t minus 2 squared. But I can factor this on the top. T plus 6 times t minus 2. Then one of the things that we know, let's start with the domain. Right, the domain of your rational functions are all real numbers except for any that would make the denominator equal to 0, because our function will not be defined when we divide by 0. And when I set that I'm not going to set it equal to 0, I can do the mental algebra to know when I set that equal to 0, there's only one answer, it's 2. So my domain goes from negative infinity to 2, and then from 2 to infinity. So that's how I write all real numbers except for the number 2. All right, the other thing that we notice about this rational function once we have factored it is that the t minus 2 on the top will cancel one of the t minus 2's on the bottom, and it leaves me that. Now, ordinarily, when you cancel a factor on the top with one on the bottom, that's the location of a hole. However, even though I did cancel this t minus 2 with one of those, there's still another t minus 2. Therefore, I really don't have a hole at x equals 2. I have a vertical asymptote at t equals 2. So I don't have any holes, no holes on that function, because there instead is a vertical asymptote at t equals 2, t being my x-axis or my independent variable. At t equals 2, we have a vertical asymptote. In AP Precalc, it wasn't good enough, and it's the same in calc, right? It's not good enough just to say that there's a vertical asymptote at t equals 2. If it's a free response question, and even in a multiple choice question, they may ask you to justify why there's a vertical asymptote at 2. And the way that you justify the presence of a vertical asymptote at 2 is you take a one-sided limit as t approaches that value of 2. And you can pick whichever one you want, the right side of 2 or the left side of 2. So I'm going to say vertical asymptote at t equals 2 because the limit as t approaches 2 from the right of d of t, limit of d of t as t approaches 2 from the right is. Now, we know what happens on rational functions at vertical asymptotes. They either go up to infinity or they sink down to negative infinity. So my answer is either infinity or negative infinity. I got to figure out which one. Don't have a calculator, don't have Desmos, got to do it on my own. What I do is I pick a number just to the right of 2, since I'm considering the limit to the right of 2. The number I'm going to pick is 2.1. I'm not going to pick 3 because there might be another 0 at 3. So I just go 0.1 to the right. If t is 2.1, my numerator will be positive. So I'll write this down, right? If t is 2.1, these are just my notes to myself. That function's value would have a positive value on the top. 2.1 plus 6 is positive. And 2.1 minus 2 is positive. And when I do a positive over a positive, I will get a positive answer. So I know that this is positive infinity. If I had chosen 2 from the left for my limit to justify the presence of there being a vertical asymptote, remember, I'm not determining if there's a vertical asymptote. I already know there is one there. I'm just mathematically writing a statement like as a proof or as justification. And because I know that the answer will be either infinity or negative infinity when I do this this one-sided limit. But if I had chosen 2 from the left, it would have been when t is 1.9, what happens? It means that my numerator would still be positive and my denominator would be negative, because 1.9 minus 2 would be negative, and then my answer would have been negative infinity. Okay, now let's move on to the end behaviors. Well, when it comes to rational functions, the end behaviors for rational functions are going to be a number if there's a horizontal asymptote. So if you can determine from the function itself if there's a horizontal asymptote, then that's going to be the end behavior of the function, both to the right and to the left. Well, when I look at this original function, it was t squared over t squared. If I multiply t minus 2 to the second out, that lowest, highest degree term is a t squared. So this is t squared over t squared. And hopefully you know that if you have a match between the degree of the numerator and the degree of the denominator, the horizontal asymptote does exist at the ratio of their coefficients, which would be the number 1 in this case, t squared over t squared. So I know that there is a horizontal asymptote at y equals 1. Now, what are the end behaviors? That tells me then that I know what my end behaviors are for the function. The limit of my function d of t as t goes to the right to infinity is the horizontal asymptote value of 1, because the function will get close to 1 the further out I go to the right. But that also means that I'm going to write the other end behavior as t goes to negative infinity. The limit of d of t as t goes to negative infinity would also be 1. So those are my 2 end behaviors. If they'd asked me the question, is there a horizontal asymptote justify? This would be my horizontal asymptote. These 2 statements are my justification for the presence of the horizontal asymptotes. All right. Now, let's go back to the zeros. That was one thing I skipped over here. I think we've answered everything. The zeros are going to be a rational function is going to be equal to 0. The y value will be 0 when the numerator of the function is 0. That's when fractions are 0, when it's 0 over something that's not 0. So the only thing that's going to make this function d of t 0 is when t is equal to negative 6, right there. T is equal to negative 6. That is an x-intercept right there. Right now, if I had to sketch this, I now know pretty much what this function has to be doing based on all of this. So I can draw myself a sketch. We got a vertical asymptote sitting over here at 2. We have a horizontal asymptote at 1. I'm going to mark that as 1. So it's crossing at 1. It's crossing at vertical asymptote is at 2. It has a 0 at negative 6 over here. So that means I know the function is coming from that asymptote. Oh, my y-intercept, that's another thing. That's another thing they could ask you for, but that's easy, right? Because that's just d of 0. D of 0 is a negative 3. I can use this up here, evaluate that when t is 0. It's negative 3, which makes total sense because it's going to be passing right here. So the function was coming here from the horizontal asymptote through the x-intercept, through the y-intercept, and then sinking down to infinity. And then over here, I did determine that when I come in from the right-hand side, it's going to infinity. So it's coming from here. So that's just the general behavior of the function. And I really knew the function wasn't down here because if it were down here, it would have had to cross through the x-axis. And there was only one x-intercept or 0 at -6. So I knew the function didn't live in that lower right-hand quadrant. It had to be up there. All right. So anyway, so that's kind of the accumulation of what they're trying to show you in AP Precalc from, I think, 1.7 to 1.10. And really, there's not a whole lot new there, right? This is pretty much what you learned in Algebra 2 when it came to rational functions, but they didn't teach you, I think it's obvious, they didn't teach you the limit stuff, right? They weren't talking about limits. No, I don't think they did in Algebra 2. They didn't teach you the limit definitions of vertical asymptotes, holes, or end behaviors. All right. I'm keeping my eye on the chat, and I don't see any questions that have come in since the photo came in on that calc question. Let's do this down here. I want to show you this problem. Rational function for sure. Let's get as far as we can in evaluating all of the properties of this thing. So I'm going to pull out the common factor. That would look like that. The bottom can be factored. Wow, interesting. So what are some things that we know? I know that my domain is all real numbers except for -5 and -3. I know that I have 2 zeros. I have a 0 at x equals 0. I have a 0 at x equals 3. Let's talk about the end behaviors and horizontal asymptotes. Those kind of go together. Because the degree on the top is larger than the degree on the bottom, 3 versus 2, there's no horizontal asymptote. It would have a slant asymptote, and I think we get to slant asymptotes in around maybe 1.12, 1.13. So I don't really want to address that right now, but I do want to talk about the end behavior. Since this function does not have a horizontal asymptote, the end behavior as x, the limit as x goes to infinity, is not a number. Because if it were a number, it would be because the function approached a horizontal asymptote. And because that degree is higher on the top than the bottom, no horizontal asymptote. So how do we know the end behaviors? Well, this is how the easiest way, this is the easiest way to do that. Easiest way is to say, well, the end behavior of this function is going to be the exact end behavior of the function that would exist as the ratio of my two highest degree terms. Like, what do you mean? I mean this. Let's just make up another function called f of x, and let's call it x cubed over x squared. Let's simplify that. That would be called the function f equals x. I think everybody here knows the end behaviors of y equals x. It goes up to the right and it goes down to the left. Those are the end behaviors. The end behavior of this function, up to the left, because it's a linear function with positive slope, down to the up to the right, down to the left, it's the same end behaviors as this function. So I now know, of course, no horizontal asymptote, but I also now know that the limit as x approaches infinity of h of x is infinity because it's going up to the right, just like y equals x is. And then I would write the other end behavior as the limit as x goes to negative infinity of h of x would be going down towards negative infinity. Let's change the problem slightly. Let's just for discussion purposes, if we're talking about end behavior, let's suppose that this was negative and this was now, suppose that term was a negative x to the fourth. There still would be no horizontal asymptote because my degree is higher on the top. But now when it comes time for me to figure out what the end behavior is, I know that this new function with that negative x to the fourth on the top, its end behavior would be the very same as the end behavior of negative x to the fourth over x to the second, which is negative x to the second. And I know that that's a parabola that opens downward. So that means as it goes to the right, it goes down. And as it goes to the left, it goes down. So both of these are going to be negative infinities. So that's how you can get the end behaviors when there's not a horizontal asymptote. And we're restricting this whole discussion to rational functions. Rational functions are ratios of polynomials. This analysis isn't the same, or it's not going to be exactly the same if I've got fractional exponents, which are not polynomials, or I got radicals involved. These are ratios of polynomials. Okay. All right. Let's see what else I had for my AP Precalc students. I think that was about it. I did have a little bit here for algebra students. And now you may say, I don't need to learn algebra 2. Well, I don't know. There's a few things here that might help you, like if you're still working on your ACT or SAT. A lot of students in algebra 2 are getting to quadratics. Either they're in it or they're about to. And I wanted to go over a few things on quadratics. A lot of this is kind of a rehash from algebra 1, maybe. But I want to show you how to graph a quadratic. Right? You should be able to graph a quadratic in, I don't know, 15 seconds, maybe. And here's how I would graph a quadratic that's in standard form. I'm first going to find the vertex, and then I'm going to use my knowledge of how quadratics behave away from the vertex. Well, the thing I need to know, if my quadratic is in standard form, and that one is ax squared plus bx plus c, I know the x coordinate of the vertex is negative b over 2a. You got to have that, right, drilled into your mind. That's what's called the axis of symmetry, that vertical line that passes through the vertex, which is also the x-intercept for the vertex. So in this case, that would be s over 2 times 1. So x equals 3. Then I'm going to go with f of 3, because I want to know the y-coordinate of the vertex. So that would be 9 minus 18 plus 11. That looks to be 2 plus 2. So that means that my vertex is at 1, 2, 3, 1, 2. Okay. This thing opens with it opens up, and it does not have a vertical stretch. What do you mean vertical stretch? If the coefficient in front of your x squared is a 1, then it's going to behave just like y equals x squared. There's not going to be a vertical stretch to it. So how do I know how quadratics deviate or move away from the vertex? I go right 1, up 1, right 2, up 2 squared, 1, 2, 3, 4, and right 3, up 3 squared, or 9, somewhere up here. And I know that it's symmetrical. I'm not going to make a table. Okay, I'm not going to make a table. And then I would sketch my parabola. Okay. Now I know my domain's all real numbers. My range is going to start at 2 and then go up to infinity. All right. What if there's a vertical stretch to it? I don't know. Let's take a look at number 7. Let's find the location of the vertex. Negative b over 2a. That's 8 over 2 times 2. I'm going to go with 2. Okay. I'll fill out that part of the table. Okay. That's my vertex. X is 2. F of 2. 8 minus 16 plus 6. Doing some mental math here. I'm thinking that's negative 2. 2 negative 2. I hope I did that right. Yep. All right. Now, how am I? First of all, this does open up. It's a positive 2. So it is going to open up, not down. But now, those moves that I was making from the vertex, right 1, up 1, right 2, up 4, right 3, up 9, all the vertical moves are doubled because of the 2 that's in front of the x squared. So I go right 1, up twice as far 2. I go right 2, but up 8, because I was going right 2, up 2 squared, or 4, but I got to go twice as far. So I go right 2, up 1, 2, 3, 4, 5, 6, 7, 8. That's all I got room for. Okay. Now, does that make sense? Look, I mean, let's just see if this even makes any sense. It looks like my y-intercept, I landed on 6. Well, sure. Look what f of 0 is. It's 6. It works. This shows me I landed exactly at 1 and 3 for the x-intercepts. Does that have x-intercepts at 1 and 3? I don't know. Let's factor out that GCF. It would be x squared minus 4x plus 3. Sure, that factors into x minus 3, x minus 1. That's why I have x-intercepts at 3 and 1. So anyways, that's my method for graphing quadratics. And then, and I'll just leave you with this thought about quadratics. If you're still doing prep on the ACT, or especially the SAT, when it comes to quadratics, you have to be able to move between standard form, vertex form, and the third form of quadratics, which is the factored form. Sometimes they present you a problem in vertex form, and your pathway to the solution is going to be to convert it from vertex form, even with some missing coefficients like A, B's, and C's. You got to multiply it out and convert it into a standard form. So those are some of the trickiest quadratic problems that you'll see on the SAT. We don't have time. I think I'm going to cut it off there. I don't have time to go any. I had some other problems here, I think, that were in vertex form, or maybe I didn't have them. No, I didn't have them here anyways. But anyway, I hope that was helpful tonight, class. I do appreciate you all coming here. I think just about everybody that was here was AP Calculus. That's why I spent more time on that. I hope it was very helpful to you. Come back next week. We'll do it again at our regular time of 8 o'clock. All right. Have a great week, everybody. See you next week.